All right, so hello everybody, welcome back. We are now going to be doing a new type of video in this course based on the feedback that I received in the in-class survey. There's a lot of great responses, but a common theme from everybody was more examples, more examples, more examples, please. So instead of doing 3 new material videos per week, we're going to do 2 new material videos per week, and that extra video slot will be optional, no new material, but we'll be going through just an example or 2. And of course, we'll still do the Wednesday material, but this will be an extra little tutorial to see how to actually use this stuff in practice. And since we were talking about diffraction theory today, we're going to do an example about diffraction. We're going to do diffraction of a laser. So diffraction theory is not just single slits and double slits and apertures. It's really a general way of treating propagating fields. Now, it turns out that if I look at the field right at the output of this laser, we often say that the light is collimated. But we find out that that's not actually the case when we dig into diffraction theory. Nothing can be perfectly collimated. There's always going to be some spread in angles, because to confine a shape to some finite region of space, necessarily that has a Fourier series, which is not a delta function. It's spread out. So there's going to be a range of angles, and it's going to spread out. So let's do a worked example today of finding out how much this laser is going to spread out. If I shoot it way over there, there's a mirror over there. Let's see if I can aim it and not blind myself. I can see that the beam is maybe a tiny bit bigger on its way back. All right, so by shining it there, we see that the beam isn't perfectly collimated, it's spread out a bit. And no matter how well we tweak it to try to collimate it, to try to minimize the spot, we'll find that there's always going to be some spread. And let's do a calculation today to figure out why that is. All right, there's an ulterior motive to do this, is that in assignment 3, I said we're going to do the Fourier transform of a Gaussian. We didn't end up doing that, so we'll do it here instead. Okay, so let's dig into this a bit. We have that beam here, and if we look at the shape of the beam right at the exit, it turns out it's what's known as a Gaussian beam. To close approximation, the electric field is this Gaussian distribution. E times e to the I. What's a Gaussian? I almost said I. E to the minus. We'll say it's centered at x equals y equals 0. So rho squared over 2 times something called w squared. And it's a 2-dimensional Gaussian. That w squared is the width of the function. So rho can be x or y, or in general, rho squared is equal to x squared plus y squared. So when rho gets all the way out to w, this field has dropped by a function of 1 over root e. So therefore the intensity is 1 over e. That's what that's the significance of this W naught here. This is the width of the beam. It's called the beam waist. The waist of the beam. Okay, well, remember diffraction theory now. Diffraction theory says I know the field of my dead laser at 0. There it is. I know the field of my laser at z equals 0. So let's solve for it somewhere downstream. And we found out that it is basically the Fourier transform. Okay, so what we're going to have to do is we're going to try to figure out the Fourier transform of this field here. All right, so let's get to that. We're going to take the Fourier transform of this field. And that's going to be some E naught times e to the x. This is rho squared is x squared plus y squared. So I can write it like this. X squared plus 2w naught squared times e to the y squared over 2w naught squared. See if you can see why that's true. Okay, and because this is separable, it's separable along time of like an x thing times a y thing. When I actually take my Fourier transform, it's just going to be the product of the x part of the Fourier transform times the y part of the Fourier transform. So we only really need to worry about one of these. All right, let's just write it out explicitly, just so you don't think I'm lying. The 2-dimensional Fourier transform was 1 over 2 pi. We're integrating along x and y, right? E to the minus x squared over 2w naught squared, e to the minus y squared. This is my f of x and y here, which is nice and separable, times e to the minus I kx times x plus ky times y. And we're integrating out x and y. Okay, so this part of the Fourier transform, I can write this as e to the minus I kx times x times e to the minus I ky times y. This part of the Fourier transform, I can pull, has just x, and this part has just y. And this part of the function has just x, and this part has just y. So let's pull all the x stuff out of that integral. And I can write that as, I'll even pull out half of a root 2. I'll see why in a second. We've got this e to the minus x squared over 2w0 squared times e to the minus I kx times x. Okay? Integrate along dx. We've pulled all the x stuff out. And then we have all the y stuff that's left over. We still have a 1 over root 2 here to contend with, so we better include it. So we'll put it in here. We have the similar integral along y, e to the minus I ky times y all times dy. Right? And this is just the Fourier transform along x. This is the one Fourier transform and the Fourier transform along y. And in this case, they're the same. So let's just look at one of these, and the result is going to be that squared. So let's just concentrate on calculating this. This is going to give us the Fourier transform of kx, right? And that's the k space. Remember, this is an angular distribution. This is going to be what the angles are distributed as in the far field. And we can convert that, as we will, to real space at the end. So let's try to calculate this, okay? So we might run into trouble. How do we calculate the Fourier transform of this? Now, generally, the integral of something squared and the integral of a e to the function of something is tough, but we have this nice Gaussian integral property such that I know this is true. E to the minus infinity to infinity, of e to the minus function, we'll call it v squared, dv, whatever that v is, that's the square root of pi, all right? So this is just a nice property of Gaussian integrals. So our goal, our strategy here is to try to manipulate this into e to the something squared, okay? So let's write down what we have. So we got 1 over the square root of 2 pi, e to the minus infinity to the plus infinity, times e to the, well, let's see what we can do here. We're going to factor out a 2w0 squared. And what do we have? Well, we have an x squared. That's good. And then I'm going to have plus 2i w0 squared kx times x. Not so good. I want to get just something that has all the x parts squared. But if we dust off the cobwebs from grade 10 or grade 11 math, I can't remember which grade this would be, there's this trick, this algebraic trick of completing the square, right? How did that go? If I have x squared plus bx, I can do this trick where I go, well, I'm going to add b over 2 squared minus b over 2 squared. And notice this then is just x plus b over 2 all squared minus whatever I added and subtracted that does not have to do with x. So minus, in this case, b squared, let's try it out, b squared over 4, all right? So we just got to complete the square, all right? If we remember how to do that. So what is b here? So it's b over 2, and we got to square that. So this thing divided by 2 squared, that I squared is going to give us a minus sign. So that's minus w0 squared squared, so to the 4th, kx squared. And that's it. That's our b term here. And we've got to add w0 to the 4th, kx squared, to be honest here. So we haven't done anything. We just added 0, right? And that's what we got to deal with. And let's see what we have here. So we have now the sum of two things, right? This is actually now equal to this thing here is what? X plus I w0 squared times k, kx all squared, plus w0 to the 4th, kx squared, the waste to the 4th times kx squared. Okay, great. Let's actually write this out now. We'll put this factor back in, and we're going to get 1 over the square root of 2 times pi This term does not involve x at all, so we're just going to be able to pull it out. So we're going to have an e to the, oh geez, let's actually figure out what this is. W naught to the fourth kx squared divided by 2 w naught squared. So this is going to be e to the minus, if I'm doing my math right, 1/2 w naught squared kx squared. And then I have the stuff that we still have to integrate out, right? We have this junk to deal with. So it's going to be e to the, let's write this in a way that's going to be very maximally convenient. So it's going to be e to the x plus I w naught squared k divided by root 2 w naught all squared dx. Why do I write it in this crazy way? Well, look, we now have something squared, a function squared here. And guess what we're going to do? We're just going to let this equal, let's use the same letter even, v. We'll let v equal this. We're going to say this is going to be called v. So v is equal to x plus I w naught squared times kx over root 2 times w naught. And therefore dv is going to be equal to, well, x over root 2 w naught. So root 2 w naught dv is whatever we would call dx. Okay, so we have this nice substitution in here. We can write this. How about the bounds of integration? Well, if x goes to infinity, so does v. If x goes to minus infinity, so does v. So our bounds of integration don't change. And we're going to get 1 over root 2 pi times, well, we have this root 2 w naught out front, integral along v now of e to the minus v squared dv. And that is our favorite integral now, the square root of pi. So this whole thing is equal to the square root of pi, which conveniently is going to cancel out this term in the denominator. So this whole term here cancels out the root pi. These two root 2's cancel. And what did I forget to write? Because I don't think it's equal to 1. This extra Gaussian term out front. E to the minus w naught squared kx squared over 2. I better write that more legibly. So let's actually bring this down now. So we now have the Fourier transform in k space of kx is equal to, we had a function out front, w naught times e to the, well, let's write this in a funny way here, kx squared divided by 2 times 1 over w naught squared. Okay? This is actually just another Gaussian. The Fourier transform of a Gaussian function is a Gaussian. The width of this is w naught squared. The width of this one, if we look at it, is 1 over w naught squared. It's inversely proportional. So the wider the Gaussian comes in space, the narrower it becomes in k space. This is something we stated without proof when we talked in terms of the time functions, the temporal Gaussian functions. Okay? So we're almost done, but I'm not quite satisfied here because I have a dead laser, but to add to my woes, not just the dead laser, which is significantly dead, is that this is in k space, but what I have in my hand here is in millimeters, not in inverse millimeters, not in angles. So let's use, here's our result right now. Let's now convert using that kx is none other than k sine theta. And that's going to be, this is 2 pi over lambda, right? And this is going to be approximately equal to theta. So it's some distance away. This theta is just going to be, for very small angles, if this is x and this is what we call z, it's going to be approximately equal to x over z. Okay? So this whole thing is 2 pi over lambda z times x. So I can replace that kx in there. All right? It looks like we're going to have to do some erasing, or I'm going to have to buy myself a bigger whiteboard. So let's do some erasing here. All right, so, okay, so what do we have now? So we have f of kx is equal to this. So we can now put this in real space, in the far field, but now I'm going to write my field along the x direction in terms of real space. So it's w naught times e to the, let's just plug it in and see what we get. We had a 1/2 kx, which is 2 pi x all squared divided by lambda over lambda z. And we have this 1 over w here. Not omega, w for waist. And that's all squared. Okay? So that's equal to e to the minus 1/2 x squared over, we'll call this that sigma z here. Actually, let's call it wz. The waist at some z. This is our Gaussian. The waist in z is this. It's lambda z over omega, or w, times 2 pi. So the waist, we'll call that wz, is equal to lambda times z divided by whatever it was at the beginning times 2 pi, 2 pi w naught. Okay, great. So that is good, right? That is what we get as a function of space. Notice that it's linearly increasing. So lambda over 2 pi w naught is linearly increasing with z. That's saying that we have a time-dependent waist. So let's plot a linearly increasing or decreasing function. That's saying that it started out as some Gaussian here. I have a width that's linearly increasing. And this is what the divergence of a laser beam looks like, right? So it's in the far field, it's just linearly diverging like this. It doesn't look like it, but it depends on what that scale is. Maybe this is a millimeter, or maybe it's a meter, or maybe it's a kilometer. If this is a kilometer and it goes up by a centimeter, it's pretty beam-like, right? So let's actually have a look at this. We actually have a waist as a function of z that has a slope of lambda. So the bigger the wavelength, the more it diverges, the more wave-like it is, over 2 pi times whatever it was at the beginning. So the tighter we tried to focus it, the more it's going to diverge, which is consistent with what we had. And the full width is just twice that. So the width of our beam is about equal to lambda over pi w naught. That's the width as a function of z, the full width as a function of z as we go out. Okay? Very cool. And this is what a Gaussian beam does. Now, it turns out that this is only valid in the far field, right? In the near field, we have to do some more math, and we may or may not do that in this course. But it turns out it just goes like this. This is exactly right in the far field, and in the near field, over some range, it's going to kind of level out. It's going to start out what looks like collimated, and it's going to very quickly go to this divergent regime. So two facts. Fact one, remember this is only along x, but we really had the Fourier transform in 2 dimensions. So in 2D, we just had to multiply those 2 Fourier transforms. You have the one in x and the one in y. That's going to go to w squared, same thing squared, times e to the minus 1/2 wz as we had before. So 1 over 2 wz squared times x squared plus y squared, or r squared. So it's still going to be a circular beam. If it started out circular, it's just going to do this in each direction. The second thing is, let's actually put a number to this. This beam, it stayed alive. Let's say the waist of this thing is 1 millimeter. I don't know, I'm just going to guess. So for example, let's just say it looks about a millimeter-ish, although it's hard to tell when looking at a beam of light. Because it depends on how much your eyes pick up. So let's say W naught is equal to 1 millimeter. The wavelength was green, so green lasers are probably around 532 nanometers. It's very common. What distance does it have to go until the waist is equal to 10 millimeters, 1 centimeter? So given this, we have a collimated beam. It seems like lasers are pretty much beams. They don't diverge. Let's see how far it has to go before this beam is diverged to 1 centimeter, which is still not much, but we'll find out it's not infinity, but it'll still go quite a distance. What distances go? Let's just plug in the numbers. We have 5.32 times 10 to the minus 7 meters divided by pi, whatever, 3.14, times 1 millimeter, 10 to the minus 3 meters. So that's equal to, we'll just approximate it. I can't do this in my head, unfortunately. 5/3 is like 1.67, so let's call this 1.7, approximately equal to 1.7 times 10 to the minus 4. Units, nothing. This is unitless. This is the slope, right? So the beam coming out is 1.7 times 10 to the minus 4. So the waist is a function of z is equal to 1.7 times 10 to the minus 4 z. And we want to find out when that's equal to 10 to the minus 2 meters. Okay? So let's just solve for that. So that's going to be z is equal to 100th, 10 to the minus 2 divided by 1.7 times 10 to the minus 4. So it's going to be 100 up top divided by 17, or 1.7. What's that going to be? Like 50, I'm just going to guess. You guys can call me on this and check. 53, 55, let's call it 55. I think it's 55. 55 meters. Okay. Ish. So this laser will go quite a way before it actually diverges. Now, if we wanted to make this stay collimated for longer, we just make the beam bigger. For example, we might be sending a laser at breakthrough starshot, which we heard a presentation about at the beginning of the class. We'd have to make the beams a bit larger so that they stayed focused for longer. But this is an application of Fourier optics to get any field. In this particular case, we calculated, given a Gaussian distribution in the near field, what do we get in the far field? The answer, another Gaussian. All right, so this has been the first tutorial video, and I'll see you guys Wednesday.